Assalamualaikum and selamat sejahtera. So today we'll continue with data processing. Alright, so another instruction is for the logic operation. Alright, so the first instruction that we're going to see here is logical AND. Okay, AND. AND stands for logical AND, in which it performs the logical AND between the content of RD and RR, and then what happens is you place the result in the destination register of RD. So by looking at this is the syntax AND RD RR, in which RD and RR can be from R0 to R31, and you see the operation here. All right, so RD and with RR and put the result into RD. Okay, let's look at this example here. Let's say like we're going to have LDI R16 for 8, for example, and then load I R17 0xAA. All right, and then let's this what we call this instruction is executed sequentially. Okay, the next instruction that we have here is AND R16 R17. So what going to happen here? All right, first for the first instruction here. All right, so LDI R16 0848. What happened is now R16 we have value 48. Right, this is in the hexa. Right, this is the hexa value. All right, and then next we have alright, so this one here goes to here. Right, okay, next load I R70 OXAA. What happened here is R17 we have value AA. Okay, before we going to do this, we need to know the what we call the truth table of logical AND. What is the truth table of logical AND? Okay, let's see lah. You put here. This is okay. We're going to do the truth table of logical AND. Alright, so you have A, B, and then this is the output F. Alright, so this is the input here 0, 0, 0, 1, 1, 0, and 1, 1. Alright, so now when 0 and with 0, what is the output of F? 0, 0, and with 1 you get 0, 1, and with 0 you get 0, while 1 and with 1 you get 1. So this is the truth table of this logical AND. Right, now since now you're going to do the AND R16 R17, so how to do that is first you need to convert this hexa value to binary number. Okay, how to do that? To do that, you are going to what we call here, you are going to use this method here, 8421 method. All right, so you have this is for okay, since this value here is 8-bit, so you have 8-bit number here. All right, so 4-bit and 4-bit. Okay, for the first number here 4, how to get number 4, how to convert from hexa 4 to binary. Right, to do that we put 0 1 0 0. Okay, what about 8? 8 is 1 0 0 and 0. Right, so this is for R16. What about R70? R70 is AA. Okay, it's AA. If you convert to decimal, AA equal to 10. So to convert to binary, AA is 1 1 and the rest 0 0. Okay, this is similar 1 0 1 0. Okay, now we're going to do the AND R16 R17. So how to do that? To do that, all right, so we are going to AND these two numbers here by looking at this truth table, so what happened here is this is a 0 and with 0 you get 0, 0 and with 1, okay, 0, 1, okay, you see here 0, 1 is 0, and then what about here, this also 0, 1 and with 1 you see 1 and with 1 you get 1, and then this is 0, 0, 0, 0. So R16 now have new number which is 0, 8. Okay, after you execute this instruction. Next, we are going to see next instruction. The next instruction is ANDI, alright, in which you want to do a logical AND with an immediate value. Okay, so this instruction performs the logical AND between the content of register RD and a constant. After that, you place the result into the destination register RD. Okay, since you see this instruction here, every time you see the instruction that ended with I, so your RD that you're going to use should be between R16 and R31 only. Okay, what about your K? K is from 0 to 55. Alright, so this is the operation. RD and with your immediate value, put the result to RD. Okay, let's. We have ANDI R16 with what value you want to put here. Okay, let's say we put FF. Alright, so this is 0x FF. Alright, so this is the immediate value. Right, so you see the immediate value is FF. Alright, so what happened here? First R16. What is the current value of R16? The current value of R16 is 08. You see here. So this is a binary representation. And then now you have a FF. So FF, this is your immediate value. So how to, what we call, to convert from hexa to binary. So FF is 15. F is 15. So 8 plus 4 plus 2 plus 1, you get 15, and this was similar. Alright, so next you're going to do the logical AND. Alright, so you need to AND these two value here, alright, between 8 and FF. How to do that? Similar to the previous one, the previous instruction. Okay, so you AND 0 with 1, you get 0. This is 0, 0. What about this one? This you get 1, 0, 0, 0, and 0. Okay, so what is your current value of R16? Now your R16 have what value? Still 0, 8. After you execute this instruction. Next instruction is OR. Alright, so OR stands for logical OR. In this instruction, it performs the logical OR between the content of your RT and RR, and after that, you place the result in the destination register of RT. Right? So this is the syntax: OR RT, comma RR, and then the operand here coming from R0 to R31. Okay, so this is the operation. You see here RDVRR. So this symbol here stands for logical OR, and put the result to RT. Okay, so now we continue with the example. We look at the example here. Okay, so you have LDI R17 with R16. Right, so now, sorry, not LDI, OR R16 R17. Okay, so now what is the current value of R16? So this is your current value of R16, which is 08. What about R17? R17 still have A. Okay, so we copied here, this value here, we put down here, and then we do the logical OR operation between R16 and R17. Okay, this is AA. Okay, so this is the R16 number, and this is your R17 number. Alright, so before we proceed with the execute this instruction, now we are going to see, alright, to see what is the truth table of logical OR. Okay, so this one is this F G. Alright, so previously we already do the A and D, and then we got to see what is logical OR, the output of logical OR. Okay, so from here, okay, so this is your input. Okay, AB is your input. 0 you OR with 0, what happened here? You get 0. What about 0 you OR with 1, you get 1. So this one here, 1 0 you get 1, and this is 1 1 you get 1. So this is the logical the truth table of logical OR. Alright, so now, okay, by looking at this R16 R17, you convert the number, alright, the hexadecimal to binary, and then you do the logical OR for each of the bit. Okay, what happened here? So you OR 0 with 0, you get 0. 0 1 you get 1. This is 0 1 1 you get 1. 0 0 0 0 1 1 0 0 you get 0, and 0 1, alright, 0 1 you get 1. Okay, so now what happened is R17 have new value. What is the value of R17? A. Okay, similar. Why similar? Because your R16 is this value here. Alright. Okay, next. Okay, so this is R17 60AA. Right, the next instruction you're going to look at is ORI. Okay, what is an ORI? ORI stands for logical OR with immediate. Okay, in this case here, you're going to do a logical OR between the content of RD and then the constant value of K, and fetch the result to RD. Right, so this is the operands. Alright, so since this one here, you see here, the instruction is ended with I, so your R that you need to use is from R16 to R31 only. While K, the constant value here can be from 0 to 255 or 0 to FF if you use the hexadecimal, and then this is the operation. Okay, so let's do an example here. So you have ORI, and then R17 with value of 55. Okay, what happened? Okay, first thing first, what is the current value of R17? So this is the current value of R17, which is AA. And then what about the constant value here? So you are going to do the logical OR with this constant value. Alright, 55. Okay, so how to do that? Okay, first thing first, you need to convert this number here to the hexadecimal number to binary. So what is the binary of 55 is 0 1 0 1 0 1 and 0 1. Okay, next, what you're going to do? Okay, you want to do the logical OR between these two numbers here, A and 55. Okay, by looking at this, what we call truth table. Okay, so by comparing this truth table, okay, you can get the value of your R17, the new value of R17, which is 0 1. You do the logical OR, you get 1. This is 1 0, also 1 0 1 1 1 0 1 0 1 1 1 0 1 is 1 and is 1. So what is the so this result here, you need to put to your R17. So R17 now have new value, which is F. Okay, so that one is for ORI. Okay, next we have the EOR. Okay, what is EOR? EOR stands for exclusive OR. Alright, so this one here, you want to perform the logical exclusive OR between content of register RD and RR. Put the result to your RD. So this is the syntax and this is the operation. Right, so we do the EOR R17 with R16. Okay, so what is the current value of R17? So this is the current value of R17, which is FF. What about R16? R16, our current value of R16 is 8. Right, so we're going to do the what we call here. Okay. So now, before we proceed here, we need to what we call here to find what is the truth table of exclusive OR. Right, so the truth table is FGH. Let's say this is H. Right, so let's this is your H. Okay, what is the truth table of logic exclusive OR? Okay, the truth table of. Okay, so before we proceed with that, okay, you need to know that. Okay, so this is what we call this is a logical expression of exclusive OR in which H equal to A exclusive OR B, in which you can simplify it by A B bar plus with A bar B. Right? So this is what we call logic expression of exclusive OR. Right? So by looking at this, you know that when you have 0, 0. Okay, so this one here, we have 0, 0, you get 0, this is 1, this is 1, and this is 0 as well. Okay, so this is the truth table of logical exclusive OR. Alright, so now EOR R17 R16. So what you're going to do is this your R16. So you want to do a logical exclusive OR between these two numbers here. Okay, by looking at this what we call truth table. So what you're going to do is, okay, so compare the input of each bit with this truth table. So 1 0, so 1 0 you get 1. Okay, 1 0 1, this 1. What about 1 1 1 1 you get 0, this is 1 1 1 and 1. So what is the current value of R7? So this result here you need to put to R70. So what is the current value of R70? The current value of R70 is F. Right, so this is 4 plus 2 plus 3, you get 7. Okay, so R70 now, okay, change from FF to F7. Okay, next. The next structure is COM. COM stands for one complement, or known as a first complement. Alright, so this structure perform a first complement of a register RD. Okay, so the syntax COM RD. RD can be from R0 to R31. Okay, you see this the operation here, FF minus with RD. Right, so let's do something like this. Okay, so you put another register, load I R18 with what value that we're going to use is 73, for example, OX73. Okay, so R18, so this is R18, register 70, whatever value that you're going to use is 733. Okay, so convert this value to 73 is 0 1 1 1, and then what about here is a 0 0 1 1. Okay, so this is your R18, and then next is you have a COM R18. So how to do that? Okay, so this is the current value of R18, which is you have a 73, and then you do the COM R18. Okay, what the first complement do? Okay, first complement to solve this to get the result of this is instruction is what you need to do is first you convert the hexa to binary number. Okay, and then from here you're going to convert this value to this value of R18 to first complement. How to do that is the first complement means that you need to invert 1 to 0, okay, and 0 to 1. Okay, so this one since it is 1, so it becomes 0. What about this one? 0, 1, 1, and this is a 0, 0, 0, and this is 1. So now your R18 have new value, which is the new value here is 8. 8 plus 4 is 12. 12 is A, B, C. Okay, 8C. Okay, or you can simply press your calculator by pressing FF minus with 8C. FF minus with 73, and you get 8C as well. Right, that is for the COM. All right, the first complement, and then we have the NEG. NEG stand for two complements. All right, so you're going to replace the content of register RT with its two complements. All right, so this is a syntax NEGRT. Okay, RT can be from R0 to R31, and the operation here you see 0, 0 minus with RT. You can simply press the calculator by put 0, 0 minus with your value from RT. Okay, let's see example here. Okay, NEG R18 for example. Okay, what is the current value of R18? R18 now is 8C. Okay, after you do the COM. Alright, so what you're going to do is, alright, so to do a second complement, alright, so this is the number of R18. To do a second complement or two complement, what you're going to do is first from right to left you need to find the first number one. Okay, so this is the first number one. Okay, so what you're going to do, you copy this number here. All right, so everything before that, before this number one, also you copy that number. Okay, what about the bit after this number one here? So what you're going to do is you convert this one here out. Okay, or you invert this bit here from 1 to 0 and 0 to 1. Okay, so this is how you do the second complement. So R18 now have new value which is 7, 4. After you do the second complement or NEG instruction, right? Or if you don't know how to do that, if you have the calculator, you just press 0, 0 minus with RT, and then you can get this value. Okay, next instruction is SBR. Alright, set bit in register. So this instruction sets specific bit in a register RT, in which you perform the logical ORI between content of the register RT and constant value and paste the result in the destination register RT. So this is the syntax SBR RT with K. So RT should be from R30 to R31 only, while K can be from 0 to 255. Okay, you see the operation here. RT do logical OR with K, put the result back to RT. Okay, for example here. Okay, so we're going to see. Okay, we're going to use the R16. Okay, so this is your R16. Okay, now what I'm going to do is I want to set this value here. Okay, because this bit 7. Okay, this bit 0, bit 1, bit 2, 3, 4, 5, 6, and 7. Okay, I want to change my bit 7 and bit 6 so that it become 1, while the rest of the bit is same. So how to do that? Alright, so this is my intended output. Alright, bits 7 and 6 1, and the rest bit is same. So how to do that? To do that, alright, I can use the SBR instruction. Right, so I use the SBR. Okay, so what register that I want to change the bit, which is R16. Alright, so what value that I going to change here? Okay, which bit that I going to change here? So now I want to change this bit and this bit only, while the rest bit is remain. So how to do that is, okay, so from here, okay, this is the value that I need to put to my K. Okay, the value of my K. So I put SBR R16 with what value here? This is a 12 if C R16 C 0. Okay, so so C0. Okay, so this is C0. This is the value of my C0, and this is the value of my R16. Okay, you see the operation here for SBR. SBR is RDO with K. So this is my K. My K is C0, and this is R16. Right. So what I'm going to do is I do the logical OR. Okay. So previously we already know that the truth table of our logical OR. So when you get 0, you have 0 input 0 0, you have 0, get 0, this one also 0 0 and 1. What about this one? 0 0, and this one was 1 and 1. So see, so the output that I get is similar to what I want it to be. Alright, so this is the SBR session in which you're going to set bit in a register, okay, to change the bit to 1. Okay, next we have the next instruction that we're going to see is CBR. Okay, CBR stands for clear bit in register. So the instruction clear specific bit in the register RD to perform the logical AND between the content of register and a constant value and place the result in the destination register. So this is syntax CBR RTK, which is your K from 0 to 255, while RD from R60 to R31. Okay, what happened here? So this is the operation RD and with FF minus with K. Let's do example here. Right. So previously, okay, so this is our current value of R16. Okay, so R16 will have the new value. So this is R16, have new value which is C8. Okay, now what I'm going to do is okay, I want to clear this bit here. Okay, so this is 0 1 2. Okay, this is D0 D1 D2 D3 D4 D5 D6 and D7. Okay, so now this is my R60. Okay, so so when I convert C8 to binary, so this is my binary number. So now I want to clear bit 3 in R16. So my output, okay, my expected output is I want to make this bit 3 0, while the other bit remains. Right, so this bit is remains, and this bit also have the same value. So how to do that? Okay, how to clear this bit 3 so that it changed from 1 to 0, but the other bits are remains. Okay, so to do that, I can use the CBR instruction. Alright, so in which this CBR clear bit in the register. Alright, so since now what I'm going to do is I want to what we call to clear this bit, okay, bit 3, so I need to put this bit 3 here become 1, okay, because I want to clear this one, so I put this value 1. What about the rest? The rest I just put 0. Okay, the rest of the bit I just put 0. Okay, why? Because the rest of the bit from D0, D1, D2, 4, 5, 6 and bit 7, I don't want the number change. Okay, I want the number remain same. Okay, so now this is your CBR. Alright, so R16. Okay, what the value I need to put here? Okay, the value that I need to put here is this value. Right? 0, 8. Okay, or x0, 8 for example. 0, x0, 8. Alright, so this is my constant value. 0, 8. Why 0, 8? Because I want to clear only this bit. Alright. So by looking at this operation, okay, what happened is, okay, you have FF minus with K first, and then after that you do logical and with RT. Okay, so okay, highlight this one, yeah, so that it become my expected output. Okay, this is my expected output. Okay, okay, so according to what we call this expression here, okay, so you have FF. What is FF? Okay, this is your FF 1111. Okay, so now you're going to minus with K. So this is your K, the constant. Okay, what you get after you minus that number, you get, okay, 1 minus 0, you get 1, this is 1, this is 1, 1 minus 1, you get 0, and this 1, 1, 1, 1. Okay, now this number here, okay, so this one here, this is FF minus with K. Okay, you get this value. So this is FF. So this is and this is your K, which is 0, 8. Okay, so now when you do FF minus K, okay, you get this number. So according to this expression, this number must end with your RT. Okay, your RT in this case here is R16. Alright, so this is your R16. Okay, we put here. Okay, and then after that, what we're going to do? We're going to do the logical AND between this number, right, and this number. Alright, so 1, 0, you do logical AND, so this one you get 0. What about this one? 0, 0. What about 0, 1? Also you get 0, 0, 0, 1, 1. You get 1. This 1. See? Okay. Your bit 3 now already clear, while the rest of the bit are similar to what we expected. Okay, our expected output down here. Okay, so this is what the CBR do. Okay, next we have the SKER. Alright, SKER. What is SKER? SKER means set all bit in register. Alright, so this is syntax SKER-RD. RD should be from R60 to R31. Okay, what happened here? FF you put to your RT. Right, so this is our current value of R16. R16, what is the value here? Is C0. Okay, let's look at this SER. This example, SER R16. What happened? Okay, you want to set all bit in register, so automatically your R16 now become 1 1 1 1 1 1 1. After you execute this instruction, because you see this operation FF, you have the value FF you put to your RD. So R16 become FF. Okay, next. The next instruction is CLR. Okay, so this instruction is used to clear the register. Alright, so see this is syntax CLR RD, in which RD exclusive OR with RD. Okay, and put the result back to your RD. Let's say lah, we want to CLR R16. What happens if you use the CLR R16? So R16 now, what happened to the value of 60? Become 0 0 0 0 0 and 0. Okay, means that you want to clear that number. Okay. And then we have TST. Alright, so this one here, TST stand for test for 0 or minus. Okay, so this TST instruction test if a register is 0 or negative, perform a logic AND between a register itself. Alright, so this one here, only you do the testing to see the to see the sign flags, negative flag and 0 flags. Okay, next, SWAP. Okay, SWAP means to swap a neighbor. Alright, this instruction swap high neighbor and low neighbor in the register. Alright, so this is the syntax swap RD. Alright, so what happened here? RD from bit 7 to bit 4 go to position RD in bit 3 to bit 0, while RD bit 3 to bit 0 go to RD bit 7 to bit 4. Okay, let's look at this example here. Okay, I put swap R18. Okay, what is the current value of R18? So this is the current value of R18. Okay, after we execute the instruction, so this is the current value of our R18. Okay, and in which R18 have 74. Okay, after you do this swap instruction, what happen is this 4 here. Okay, here we go. So this is the in the hash. What happened is bit 0 to bit 3. So this is bit 0, bit 2, bit 3. We swap of position to bit 7 to bit 4. Okay, while this bit 4 to bit 7 will swap position with here. So what happened is your R18 now have new value 47. Okay, you do a swap operation. And last but not least is NOP. So NOP stands for no operation. So this one here, you just want to do nothing. Alright, you want to do nothing, or you want to waste thing